All right, we're back. We're on page 3 of notes 19 of Calc AB, where you're talking about motion and antiderivatives, but we're also talking about motion and derivatives. So there's a lot of velocity, acceleration, speed, distance traveled, displacement questions going on. Those are the things I think of when I think of motion and calculus. So let's see what we can do. So we got the velocity of a particle moving along the x-axis is modeled by a differentiable function v, where x is measured in feet and t is measured in seconds. All right, so good stuff. Selected values of v of t are given in the table. The particle's position is x equals 4 at t equals 0. So this is probably going to come into, oh, you're not a pointer. This is probably going to come into play at some point. Estimate the acceleration of the particle at t equals 12 seconds. Show the computations, indicate units of measure. Super common problem. So I'm going to say that a of, so now here's the thing. So I'm going to just say like a of t is equal to v prime of t. And so the reason that I'm saying that is like you're supposed to connect acceleration to velocity and connect velocity to position. And so I'm just getting that out of the way. And then I'm going to say that a of 12, not 1.2. A of 12 is approximately v of, all right, 12 is in between 18 and 6. So 18 minus v of 6 over 18 minus 6, which equals v, so negative 8, let's show it, negative, ew, let's do negative 8, where are you? Negative 8 minus negative 4 over 12. Negative 8 plus 4, negative 4 over 12, negative 1/3. What are our units? Well, x is measured in feet, t is measured in seconds. So that means that velocity is in feet per second. And so we have feet per second divided by second. So I'm going to say feet per second squared. Actually, I'm going to say feet per second per second. Feet per second per second. That's my preference. I prefer to write it that way. I think that seconds squared don't make any sense. So I like to say feet per second because I think it's easier to interpret. All right, let's look at the next thing. Using correct units, explain the meaning of the integral from 6 to 24 v of t dt in the context of the problem. So like, don't just explain it. We got to like, say in this problem, the thing did something. Use a trapezoidal sum with two subintervals indicated by the data to approximate 6 to 24. Okay, so first, let's interpret this. So this integral of velocity gives you displacement. Integral of the absolute value of velocity gives you distance traveled. So this is going to be displacement. So I'm going to say on the time interval from seconds, so t equals 6 seconds to t equals 24 seconds. Or I'm going to just say the integral represents the displacement of the particle on the time interval from t equals 6 to t equals 24. I'm going to say the displacement in feet. So 6 to 24 of v of t dt represents the displacement in feet of the part, ew, what? It's like I invented a word, oath, of the particle on the time interval. So much writing. Calculus, all writing, man. Like you usually like know the answer and it's like, now how do I say it the best? On the time interval from t equals 6 seconds. Seconds? Minutes? I don't even remember anymore. Seconds to t equals 24 seconds. Okay, that's definitely what it represents. Now I'll find the value, and then at the end I might say like, so the object is, so the particle is whatever feet to the left or feet to the right or something. Let's do it. So 6 to 24 v of t dt. We're approximating, right? So approximately equal to, we're doing trapezoids, so 1/2, and then I'm going to do, all right, so we're going to do we're going 6 to 24. So from here to here is 12. And then I add up these to get negative 12 plus from here here to here is 6. And then I add up these and I get -9. Okay, so this is going to be measured in feet. So this is where I hate the rule about you don't have to simplify. Like technically you don't need to simplify this, but like then how do you say what you are? Like your feet. Okay, so I'm going to simplify it and get 6 times -6 is -70. I don't know what I'm saying. 6 times -12 is -72. And then 3 times -9 is -27. So I get -99. This is in feet. So I'm going to say the particle, I guess it's a particle. The particle, so is an object or a particle, is 99 feet to the left of where it started. At t equals 6 seconds. So like at t equals, I should probably say at t equals 24. At t equals 24 seconds, comma, the particle is 99 feet to the left of where it started at t equals 6 seconds. I think that's a good answer. The only thing that could be wrong with it is I could have gotten this number wrong, which I hope I didn't, but you never know. I don't know, 54 plus 144 is 198 divided by 2, 99. I think it's good. All right. For 0 to 30, must the particle change direction in any of the subintervals indicated by the data? If so, identify the subintervals, explain your reasoning. If not, explain why not. Let's see if velocity changes sign, because if velocity changes sign and velocity is continuous, then the particle must, well, actually, the velocity changes sign. You don't actually need it to be continuous. I believe that the velocity is continuous because the velocity is differentiable, but I see here we have a sign change. So a sign change would indicate a change of direction. So on 0 to 6, there's a sign change, and on 24 to 30, there's a sign change. So I'm going to say, what am I going to say? Must the particle, yes, the particle must change direction. So yes, the particle changes direction on, so we said on 0 to 6 for sure. And then also, so, I learned the other day that I could do this. I'm going to like steal this and bring it down with me, use it, and then I'll delete it. So I'm going to copy that. Look at this magic. And then I'm going to paste the image. And now I can kind of just like look at it and kind of use it while it's there. Oh my God. I've recorded like 200 hours of videos and then I learned I can do that. Doesn't speak well of me. Changes direction on 0, 6, because I'm going to say like, because v of t has a sign change. Let's do multiple at the same time. So let's save the because, and then we'll say all end on 24 to 30. 24 to 30, because v of t has a sign change on those intervals. So there are definitely 2 times that we change direction. We don't really know when they are, but it's a fact. I'm gonna bring this down here. Look at this. Also, I'm apparently, oh no, I stole my v of, how is that possible? Uh-oh, is this a little trickier than I thought it was? There, and then I move it, and why is that connected? Whatever, let's just fill this in, and then we'll delete it. Get out of there. Okay, here we go. Suppose that acceleration of the particle is negative between 0 and 6. Explain why the particle's position at t equals 6 must be less than 35. All right, well, I'd love to know where it is at t equals 0, so let's go back up and read that. At t equals 0, we are at x equals 4. I think I can write an accumulation function here and think about that. So at t equals 0, x equals 4. So in general, at x of t, we're going to be 4 plus integral from 0 to t of v of dummy variable v of u du. That's the true position. Now, explain why it's less than 35. All right. I tend to like to think in extremes in this situation. So we know acceleration is negative, which means velocity is decreasing. So since a of t is less than 0, v of t is decreasing on 0 to 6. All right. I'm just really stating something, but putting it in the context of the problem. I'm going to say, therefore, v of t has max value of 5, and that occurs at t equals 0. So what's happening is we're starting at a velocity of 5, and then it's got to decrease everywhere. So what I'm going to do is I'm going to look and see, well, if the velocity was always 5, would I get to 35? And if not, then when the velocity is less than that, I'm never going to get there. So at this point, I think I can definitely say that the integral from 0 to 6 of v of t dt is less than, I mean, I could say less than or equal to, but it's definitely less than the integral from 0 to 6 of 5 dt, which is equal to 5 times 6, so 30. Okay, so then 4 plus the integral from 0 to 6 of v of t dt is less than 4 plus 30, which is 34. And this is x of 6. So think about what we did. We said, this is definitely your position. So x of 6 is definitely going to be 4 plus the integral from 0 to 6 of v of t dt. Now, 4 plus the integral from 0 to 6 of v of t dt is less than 4 plus the integral from 0 to 6 of 5 dt, right? Because v of t is always, well, it's less than 5 everywhere except at 0 where it's equal to 5. So that's definitely a true inequality. This is 34, so it is definitely the case that x of 6 is less than 34. Therefore, the position at t equals 6 cannot be 35. There's no way. Can't be it, because even if we were going as fast as we were capable of going on the interval, the entire interval, we only get to 34. So definitely not going to be 35. It's kind of a common question, actually. Well, not common, but like it comes up. They like to ask about the, what do they like to, oh, like the absolute maximum, absolute minimum, right? Like a different type of question. We might have found the absolute maximum, and the absolute maximum would have been like less than 35. Or maybe the absolute maximum is greater than 35, and then we're like, oh, intermediate value theorem. So a lot of things to like think about as you're doing these, but like read the question, follow what it tells you, and try to apply it. So the key thing there was that the velocity was decreasing. And they told you that indirectly by telling you about acceleration. You have to connect the two. All right, so I'm gonna end this here. I'll be back in the next video, and I will see you there.